right. Hi, everyone. Happy Tuesday. We are going to continue on with the example problem that we're doing, and we're going to look at a final cumulative damage rule that assumes we have periods of a loading spectrum that we can pull out and identify. So each period will have its own sort of characteristics, right? So the example problem that we had was a bar that was undergoing cycles, and it had specific loading and certain number of cycles, and then another loading and then another number of cycles, and these were axial loads. And we applied sort of a cumulative damage rule. That was, the first one that we did was this Markov-Starkey cumulative damage, and it was independent of the order in which those loads were applied. So we had A, B, and C loading regimes, and we just sort of lumped them all together. The second one we considered was the Henry cumulative damage model. And in that model, the order mattered. So we had those regimes A, B, and C, and A was the highest load. And so what we did is we looked at that phase of high loading and then intermediate and then low loading for a long number of cycles. And we determined that the bar would not last the full spectrum of loading if the order matters, right? Because there is a history dependence where if you induce a certain amount of damage, you can't go back. And that affects the further damage. And the way that we accounted for that was to modify the endurance limit and move that SN curve down with subsequent damage until eventually there was no more y-axis to move down, and then we determined that it would experience a fatigue failure. So I want to cover one final model today that we'll also use in that sort of same iterative sense. And this one is called the Manson double linear damage rule. And what it's going to do is going to set us up for dealing with cracks. So far, we haven't really talked about the cracks themselves, right? The size of the crack propagation as a mechanism. We've sort of said we're just going to talk about a fatigue failure, right? The thing is in operation, we're not inspecting it at all, and then all of a sudden it fails, right? And so this double linear damage rule is one way to try to account for that. The fact that some damage goes into building up those dislocations and building up the slip planes, and then eventually initiating a crack. That's the first phase. Second phase is crack propagation. And so without a knowledge of the crack size and the cracks themselves, and looking at the fracture mechanics specifically, this theory was proposed in about 1965, 1967. And it basically deals with cracks by just saying we have two regimes, two ways that damage is going to build up. And so there's two phases, right? So the first phase, phase one, damage goes toward initiating a crack. And then once there's a defect there, once there's a crack, then we move to phase two, where the crack propagates to failure. Component failure, right? Crack propagates all the way through. And so these two phases are represented by partitioning the number of cycles to a fatigue failure, right? So before we had kind of the SN curves like this, and we would just look and say, okay, at X number of cycles, we have, or at Y stress level, this component will last X number of cycles, right? And so that was a complete failure. And so now we're going to break up that N, how many total cycles we can sustain, into these two phases. So here's what Manson proposed. He said the number of cycles that it takes to propagate a crack can be represented by a power law that is related to the total number of cycles. So NF is going to be the total number of cycles to failure. So that's kind of our like sigma F, kind of what we've been sigma N, kind of what we've been working with, right? That's the total number of cycles to failure. And so if we put that to some power, of course we're going to have similar variables here, but a small p, and then we just have a coefficient out front, large P, then if we can determine these constants experimentally, then we can sort of do this prediction of these two phases and how they accumulate. So we'll determine these numbers experimentally. Okay. And then we can do some writing, right? So we say now that the number of initial cycles, which I don't know why we have instead of a subscript, they use a prime. So the number of cycles for initiating the crack, the first phase, is going to be equal to the total number, NF, minus that number in the second phase, NP. And then we can substitute in the expression that we just had. So now it's NF minus capital P times NF to the lowercase p power. So we start to get some of these relationships. And now this one's just in terms of the overall number and then these experimental coefficients. Okay. So this is good. And then so Manson proposed this, and he said, I'm going to run like tons of experiments to try to come up with what are the characteristic constants here that we're going to use. So the power coefficient, and then also that the coefficient out front. And so I'm just going to tell you what he selected. So for, I guess, most ductile metals, he said that the power was going to be about 0.6. And it says based on an integrated consideration of data for many different materials. Okay, so many materials. And then the coefficient out front, this uppercase P, he determined to be a value of 14. All right, so now you're seeing how these, this damage theory is very empirical, right? So there would clearly not be like 14.000 out here in front, but this was determined from best fits to testing at 2 stress levels. Yeah, so 2 stress level spectrum testing. All right. Where first you run it at high stress for some number of cycles, and then the second level is lower stress, or you flip that and then you do lower stress and then higher stress. Okay, so then if we write these equations, we could say, just plugging in numbers, okay, N prime is equal to NF minus 14 times NF, to the 0.6 power. Okay. And then there's a further limit that he put on this. And it basically is just a limit for his number of cycles for high cycle fatigue versus low cycle fatigue. So for these equations, this is relevant for anything. These numbers are super empirical, greater than 730 cycles. So there you go. Okay. So based on this, like, we have to then come up with some damage fraction, right? And so you can write the failure criteria as this, like fatigue, let's call them defects or cracks of some critical size, like where it transitions from phase 1 to phase 2, right, are initiated when we add everything up from I equals 1 up to m of our damage fraction of the first phase. So it's this n prime, right, that we're comparing to. And then fatigue cracks are propagated if the first condition has been met, and then also we sum up from, they have different subscripts, j equal 1 up to q of n, sorry, that should be little n j, divide by the number of cycles in that second phase, np, right, when that equals 1. So first we start with this equation here, right? We'll call it, like, for phase 1. I'll just do a little circle next to it. So we start with that one, and then we say when that reaches 1, then a critical crack has formed. And then we start applying equation number 2 and determine how many more cycles we have until we would expect the thing to fully fail. And then there are some plots in the textbook. You can look at them in figure 8-10, but they're not critical. They're just the 2 stress level results that Manson was fitting to come up with these coefficients. You will see that they sort of barely fit, but this was the best that he had at the time. Okay, so let's think about our problem that we had and see if this double linear fatigue model, when applied to these loading levels that are repeated 3 times, let's see if the system will last according to this theory. So we had 3 load levels, right, A, B, and C, that were kind of 22. I'm gonna put that in kilopounds. 22 kilopounds, 12, and 6.5. And then we're gonna choose an area that was similar to the areas that we calculated last time. So we're gonna use 0.15, and that's in inches squared. And that's gonna be the same for all of them, which means our first, so the first time, whoops, I don't know where that spike came from. Our stresses, right, this is an axial stress. So we'll do K PSI here. And these are the same as we calculated for some of the other ones. So 146.7, 80, and 43.3. That's just the load divided by area. Super simple. And then we would go back and look at the number of cycles to failure from the SN curve, the initial SN curve, and just read it off for those stress levels. So for the first stress level, right, we would get about 4,500 cycles. And the second stress level is much lower. So we get 445,000 cycles. And then for load level C, right, on our other ones, we had that was below the endurance limit, so we last infinite number of cycles. Okay, and so I'm going to move down because I sort of run out of room to keep going across. So now let's take that number of cycles to failure to the 0.6 power. for each load level. And so all we do is take 4,500 to the 0.6 power, we get about 156. Similarly for the second one, we get 2450, and then still infinity to the 0.6 power is still infinity. So this is sort of just that. And then we can multiply it times 14 to get that number of cycles in the second phase. So how many cycles we would expect it to last when the crack is propagating. So if we do that, we get 2180, 34,300, and infinity. And so this is the second phase, how many cycles we would expect to get. And then if we know the total and we know the second phase, then we can calculate how many cycles we would expect to get in the first phase at each stress level. So all we do is take NF, subtract NP, and we come up with this. So we'll say 2320, 410,700, and right, it would last infinity there. So this is the first phase. Okay. So we haven't talked about the order in which these things are really applied yet. Just at each load level, this is what we would expect for these partitioned into these two phases. So now we can look and start applying those loads and then calculate the damage fraction at each one, that little n divided by big N, because we had a certain number of cycles that we were running at these different stress levels. Okay, so I'm going to try to put this over here in a little chart. So let's apply load level A, and that had a certain stress level and number of cycles that were allowable. And so our number of cycles that we applied from the problem statement was 1,200. And we're still in phase one now. So we're not talking about the crack propagation. So if we're talking about just the damage accumulation to crack initiation, we could do 2,320 cycles, right? That was our N prime. So our damage, N over N prime, is going to be 0.517. Okay, so we're a little over halfway to initiating a critical size crack. Okay, now we go to application at load level B. So it's a much lower stress, and we applied that one for 7,000 cycles. But we had a really high number of cycles that were allowable there, like 400,000, greater than 400,000. So our fraction there is super small. It's like 0.017. So our total so far is like 0.534. So, okay, so we have not yet gotten a critical crack, which is good. We haven't even gotten through one phase of this. Then we go to load level C, where we're applying 50,000 cycles, but we have infinity we can apply, so that adds nothing to our damage. So we're still at 0.534. And now we get to the second load level, or the second time through these loads. So now we need to apply another 1,200, right, at this load level, and we're still below, so we're still on the 2320. So now we add another 0.517, right? So you can see now, if we add that 0.517 to our 0.534, now we have initiated a critical crack. So thus we can say that we would expect a crack to form at this point, and we can clearly see that we're not going to make it through without propagating that crack, because if we go over to the second set of cycles in phase 2. I'm just going to like circle that here. Right, if we go over to NP now and look at how many cycles we're applying and how many are allowable in that phase, it's fewer than we have been allowed. Right, so that means the proportion of our damage accumulation is going to go way up. So the book actually doesn't even, they stop the example right here because we've reached our over 1 for the crack initiation. And then if we keep going in the second phase, then we'll clearly reach that very quickly because we're not even on the third set of these loads. And so this means that the area that we've selected on this one is too small. If we selected a cross-sectional area that was bigger, we could go back to our SN diagram. We would get a longer life at these load levels, and then the fractions that we would get would be much smaller in the damage accumulation. And so these three, the three sort of accumulated damage theories that we've talked about, I just want to emphasize that they apply to situations where we can break the loading up into these different phases that have characteristic loading. This is not for like random loading, right? We're not doing like 1 cycle by 1 cycle by 1 cycle, right? That doesn't make sense. But if we have X amount, like thousands at some load level, and then another X amount of thousands, these kind of damage accumulation theories can describe those very accurately if the materials and the way that the theories were developed are well suited to that. And so you can see that the theories, as we went through them, got more and more empirical, right? They had these constants of 14 and 0.6 and things like that were just from fitting to lots and lots of data. And so that's why most people use, when they're doing a first pass approximation, they go back to the linear, just the Palmgren-Minor, linear superposition of the damage to calculate that. Yes?
Because we are looking at N over N prime to just be 1 for the crack initiation, right? If A had a lot of cycles of that N over N becomes 1.5, in one example, do you divide that cycle to take the other half to the crack propagation region? Or just
Yes. So the question is, if we reach some damage accumulation over 1 for the first phase, then can we say that it stops at a value of 1, and then the additional cycles that are remaining there get shifted to the second phase? And the answer is yes. So if we were to continue on, we could apply sort of this phase. We could see how many cycles of this 1200 would be left after, how many of those 1200 would be needed to reach exactly 1 on the damage fraction. And then any subsequent cycles would then start. So maybe that's, I don't know, something like 1100, right? Something like that. And then we would go to our next, we'd have like another phase A here, but there would only be 100 cycles. And our allowable would be 2180. And then we would continue calculating from 0. We'd start over again in our phase 2 calculations from there and go downward. And then once we reached 1 again, we would predict the whole thing has collapsed. Good question. Okay. So that's the double linear damage rule. And so I'm going to shift gears here, and I want to give a case study. Give me 1 second here. That shows kind of the progression of the study of fatigue failures. And I took this from Dr. Eric Kyrie's notes. So he's taught this class many times, and he was an expert in fatigue and specifically how to apply it to new cases and things like that. So I want to just do like a little bit of story time and talk about this case study because you will understand a lot about it from the things that we've studied so far, and it also motivates us talking about fracture mechanics and crack propagation in order to map this out a little bit better. So this case study is about fatigue failures of the de Havilland Comet aircraft. And so I mentioned to you that the last damage, accumulation damage model we looked at was proposed in 1965. And so this aircraft, the first one, was developed, come on, okay, in 1952. And so it started being designed in the late 1940s after World War II because of new technologies that came out and new jet engines that could go a lot faster. And so there was a need also to employ a lot of people who had engineering experience from World War II. And so this company, de Havilland, decided to make a jet engine commercial airliner. And it was a small jet, so it could only carry 36 passengers, but it would go really fast, like 500 miles an hour. And it had a very long range, right? So this was like going to be a state-of-the-art thing. And because it flew so fast, it had to fly at a very high altitude. So it flew at like 40,000 feet, which was much higher than other aircraft. So because of that, they had to pressurize the cabin. So before that time, when you think about like, I don't know, World War II era aircraft, they didn't fly high enough to have to pressurize the cabin, and people could still breathe inside of them. But once you got this high, the cabins had to be pressurized. And so it introduced different modes on the fuselage that had to be accounted for, and specifically stresses due to this difference in pressure. So sorry to be the bearer of bad news, but the first iteration of this Comet aircraft was a failure because multiple ended with fatal air crashes where basically the fuselage came apart mid-flight before it was expected to, right? So it came apart when there had been like between 1,000 and 1,500 flights as opposed to 10,000 flights, which is how long it was supposed to last. And so it's an interesting case study. So here's a picture of this aircraft. And these slides are directly from Professor Eric Carey and some of the research reports that were written on this aircraft. So you can see the jet engines mounted within the wings, and then you can notice that the windows are square-ish. There'll be a lot of focus on that in this presentation, but the contribution of these window shapes is, I would say, under contention from more recent theories. So some of the design details. As I said, this was right after World War II, so construction techniques were a mix of old and new. Rivets were used in some areas, but also adhesives to glue multiple layers together because they wanted to have the skin of the aircraft be very light. Right? It was also the first time that hydraulic actuators were used for all of the flaps and the control surfaces. So before that, the pilots actually had controls that were attached by mechanical wires to the flaps. So they could feel the resistance to some extent when they went to move the flaps. But when you now have hydraulic actuators for that, the pilots lose that sort of haptic feedback, right? And so they felt, the pilots flying these planes had to be trained differently, and they felt a little bit less like they were in control of the plane, so that didn't help. The cabin was pressurized to 8,000 feet. So it was flying at 40,000, but it was pressurized to 8,000, which gave a pressure differential of 8.65 psi at cruising altitude. So this was double of other commercial aircraft at the time. And then the windows were rectangular-ish, right? We'll talk about that in a minute. It was based on sort of planes that had been used to just deliver packages in the past. As I said, it started in the late 1940s, the design work, and the key features were that it was going to be super light aluminum construction, as I said, hydraulic actuation, 4 jet engines, small number of passengers, long range, high speed, high cruising altitude, and those kind of things. But there were a series of fatal crashes that happened, and some were hard to figure out why they happened because they coincided with bad weather and high winds. And there was actually a plane crash, a day or two ago, that happened in Toronto because in part of high winds, and so that can be a real problem. And so there was some confounding factors there, but overall, the pieces were sort of retrieved after some of these mid-air explosions, and it was determined that the fatigue failure of the outside of the fuselage was the problem. And so here is a picture from a laboratory failure. So this was not retrieved from some kind of a crash site, but rather this was done in a laboratory. And so this is the inside of the fuselage with all of the, I guess, all of the seats and the walls and the vents and all that stuff stripped. So this is just the outside, and this is the structural component. So you can see there's a rectangular window with rounded edges, but the cracks that occurred sort of propagated across. They could have initiated near the window, they could have initiated elsewhere, but they went right through the side there and caused these catastrophic failures. So we've been looking at thin-walled pressure vessels, and so this is not, we're not going to model this or something like that, but this is the background of estimating the kind of stresses that were around the fuselage. So if we look at hoop stress and longitudinal stress, we find that the biggest stress is the hoop stress. And so for a diameter of 8 feet, a wall thickness of 0.03 inches, so it's very thin, it's less than a millimeter, and because it's so thin, it's actually sheet metal, right? And they specify the thickness of sheet metal in gauge. So it's 22 gauge. There's a pressure inside, right? So that was readily known. And so we could calculate S1 to be something like 126 megapascals. And so the fatigue testing that was done on these was twofold. The first phase was actually not fatigue testing, but the first phase that was required by the British safety testing was that this structure had to be pressurized to 2 times the operating pressure and not burst. So that was kind of like a quasi-static test. So they said, okay, it's going to be pressurized in flight. We're going to pressurize it to double the pressure, and then if it doesn't have any damage, it passes that test. So that was the first thing they did. The second thing they did was a fatigue test where they then put it under cyclic loading for X number of cycles, right? So that would be supposed to be simulating how many flights it would take, okay? And so what they did was to satisfy this, they said, we're only going to make a certain amount of these prototypes and test models, right? We're not doing this multiple times. And so what they did is they used the same specimen for the initial pressure test and then for the fatigue testing, right? And so that should be sort of like having some bells go off in your head of what were the stresses if they doubled the pressure inside, because we know the stresses are directly proportional to the pressure inside, right? And so we might expect there to be some permanent change in the material before they went ahead and did the fatigue test, and then that would not represent the real situation of the production specimens, right? So when these three terrible crashes happened, it revolutionized sort of the recovery efforts and the engineering of what happened to try to figure out where the engineering had gone wrong, because this was a repeatable failure. So one thing that they did is they grounded all of the aircraft that were in operation, because they didn't want to have any more fatal crashes. And they said, we're going to take one of the ones that's already been in operation. So it had accumulated 1,221 internal pressurization cycles in service. And then they put it in a water tank where they added an additional 1,800 cycles before they observed the same sort of cabin ripping open. And then they were able to, because they did that in a laboratory, look where did the cracks initiate and what happened. And so the laboratory testing, right, revealed that the origins of the fatigue failure were around the edges of the windows, in part, not all of them, but there was some evidence here. And the way that they looked at this was so here's obviously the plane, and the first red arrow shows you, the window. And then the second arrow goes down to show you just that little rounded bit of the window. And so they marked out all of these locations that they wanted to look at, because they knew that the failures had occurred near the windows, but they didn't know exactly what was happening. So they marked out specific locations, and then they slapped strain gauges on the outside of the fuselage. So if you look at this grayed out image here, that's a cross section that they took directly from, like, if you're looking sort of at the plane window. And then if you take a section from AB, which is here, down to CD, which is here, there's also a curvature out of plane, right? And so they stuck, and that's what's shown on this where it says out of plane bending, right? So there's out of plane just means in and out of the page here, right? And so there's a little bit of curvature there as well. So they put strain gauges there, and they found that near the window corners there was an increase in the magnitude of stress that they had not initially calculated. And so I think I have this on. Nope, I don't have it on the next slide. But they did this at multiple locations. And so the procedure at the time was to do this pressurization testing and say, okay, it's not going to fail due to pressure, and then do the fatigue testing to say that it should last X amount of flights, in this case, 10,000. And so that design against fatigue failure was called a safe life approach. And so they said, as long as we just inspect it frequently as it approaches that 10,000th flight, we should be fine, and we can fix any cracks that are there. And so they continued to look into the forensics of where it failed. And so if you follow the pictures here, you can see inside of the fuselage. So this is the outer, if we look at sort of this picture on the top here, I'll just circle it, right? So that's what the inside of the fuselage looked like. It had the outside, and then it had frame pieces going vertically, and then it had stringers going across, right? And the way that all of these things were attached together is that they were riveted. And they were riveted, so if you look at this second picture here, where it says cut out in frame, you'll see that there's a lap joint where I'm sort of pointing right here, where the stringers have a flat section, a land, that meets the stringer geometry, and then that all is riveted to the outside. And so there are holes, many holes to distribute the stress, but still holes going through there. And so you can see if they then look in a downward view on this bottom left picture here, sort of if you're looking down at this second picture here, you'll see that there are some rivet holes, right? And so all of the little holes that you see there are rivet holes from attaching either the window, right, along that curved edge, or these stringers and frame pieces along the inside. And here's a cross-section view of what these rivets looked like. So they were riveted from the outside to the inside. And so the larger section, which is called a knife edge countersink, was at the outside. So when you look at the outside of the fuselage, it looks smooth, right? The rivet is the same plane as the outside. And so this is what everything kind of looked like. And I want to sort of think more about the stress concentrations that happened around those rivets there, and all the loads that were applied. So if you think about this fuselage and the internal pressurization, right? So the internal pressurization happens, and so there's a tensile hoop stress around, and all of these stringers provided resistance to that expansion. And so they provide a load P that goes the opposite way, and so they provided sort of a resistance to that, right? And so that's where there's a high stress around those rivets. Hang on a second. Okay, so I'm going to go to this slide first. And so in undergraduate, when you start learning about stresses, right, and so let's say we just have a plate and we're applying an axial stress. You could imagine that that is the plate that is experiencing a hoop stress around the fuselage, right? Well, now we put a hole in it, and we're still pulling on it. There's a stress concentration at that hole. And so this top left plot is a multiplication factor, right? Stress concentration factor, KT, that you multiply times the nominal stress to get the true stress around that hole, right? So it's KT times the nominal stress. And so the bottom pictures here show the increase in stress around the hole. So this dark section here that you see is a graphical representation. It's not a physical thing, but it's a graphical representation of the local stresses around that hole in the middle. So you can see that they sort of asymptotically go up to some maximum KT times the nominal stress. And so this is important for this situation, thinking about the fuselage, because when they initially tested in the laboratory, they pumped that thing up to double the pressurization of the inside, which means double the stresses. And so they probably had a little bit of clipping because they probably hit the yield stress. Okay, so you can't apply a stress in the elastic regime that's beyond the yield stress, right? So those plots where it shows the stress going up would be clipped there at the yield stress. So let's say that when they pressurize it to double, they have a little bit of plastic deformation yielding around the sides of that hole. But they don't really think about it because it's so distributed, they don't see a crack. And so then they release the pressure back down. Well, when they release the pressure back down and they have had a plastic event, they induce residual stresses around the defect. So around the hole is now a compressive residual stress, right? So internal to the plate around that hole is a compressive residual stress. And so because of that, then if you pressurize it again, and now you induce a second tensile stress, you start from a negative value. And so you don't get the type of damage that you would have gotten otherwise because of this compressive residual stress after unloading. So, all right, 5 minutes. So if they pressurized it and then they depressurized it, then they would have yielded the area around the, potentially around the rivets, creating a small compressive residual stress such that when they then loaded it for the fatigue testing, right, the level they thought they were loading it to, they were not because of this compressive stress that was already there. And so they said, oh, it's going to last 10,000 flights. But in fact, the stress levels that they were applying were lower than they thought. And so, sure, it would last 10,000 cycles at a lower stress level, but not at the stress levels that they experienced in flight, and because they had not done that double pressurization test to get it up there. And so this is a paper that I found, which I really liked. It shows the cross section of laminate metals that have been deformed by a punch rivet. And so this was the type of rivets that were used to put these aircraft structures together. And you can see that when they punch in a rivet, there's a lot of deformation of these layers, like significant deformation, right? Such that there's an overhang and what they're calling an interlock, right, of these layers that keeps it from pulling out. And so there's significant deformation that happens. And there is an engineer that went back, I think like in 2007, and he started thinking about this particular design. And he said that these punch rivets were very commonly used, and sometimes they would induce small cracks in the materials that were missed before these pieces went into operation, right? And so there already were likely some very small defects in these structures before they even went into operation. So because of this particular model and these particular failures, in the late 1950s, after that, they changed from the safe life design to a fail-safe design philosophy, where they built in sort of this cascading structure of, okay, if the outside fuselage fails, then those stresses will be taken on by a secondary system, which will then be taken on by a tertiary system, such that there isn't this massive failure and loss of life. More calculations are done, and the whole structure is more damage resistant. So shortly after that, that comet failure came some really popular models like the Boeing 707, and it actually still had squarish windows. So this is where some of the contention comes in. Some people say, oh, that first plane had square windows and that's where everything failed. Not necessarily. It had a lot to do with the rivets as well. And other planes subsequently had square windows and they were highly successful. So it's not all due to the square or square-ish windows. So I'm going to finish there today. And yep, that's the last slide. So thanks. I'll see you back on Thursday. Yeah. All right.